Hi, my name is Gina Porter, and I am the math specialist here at Rock Prairie Elementary. And for the next few minutes, we're going to talk about second grade math and one of the topics that they're talking about during the second 9 weeks in second grade, specifically addition and subtraction with non-standard algorithms. So first, let's look at the overview of the whole second 9 weeks. They're going to start off with addition and subtraction with non-standard algorithms, which they actually started in the last part of the first 9 weeks. So they've been doing it a while, and they will continue to do it through the first few weeks of the second 9 weeks. Then they're going to move into organizing and interpreting data, which is looking at graphs and creating graphs. Then they'll work on telling time to the nearest 5 minutes, and finally they will work on fractions, on recognizing and representing fractions. In order to successfully add and subtract numbers, we really have to have a good understanding of the numbers. And so one of the things that we ask them to do is to work with an open number line, and they've been doing this for a while. An open number line is just a line with few or maybe even no numbers on it. And we use it to help them develop and demonstrate their number sense. So if we look at this number line here, we see that it's marked with 70, 80, and 90. So if a student is asked to place 82 in the appropriate place on the number line, first they have to think that it belongs between 80 and 90. And then they have to understand that 82 is much closer to 80 than it is to 90. So in the top number line, 82 is placed appropriately, and on the bottom number line, 82 would be way too close to 90 and not close enough to 80. So again, we're using this to demonstrate understanding of numbers. We're also going to use it as a tool to convey our thinking while we're adding and subtracting. Here's an open number line that a student might be given with no numbers on it originally, and the student is asked to place three numbers, 49, 57, and 88, in the appropriate place on the number line below. So what they have to consider first is that the order that these three numbers belong in and the magnitude of the numbers. The fact that 49 and 57 are relatively close to each other, but 57 and 88 are much farther apart from each other. And so if we look at the top number line, we see that the student considered that when they placed the numbers on there, that they put 49 and 57 much closer to each other than they placed 57 and 88. And on the bottom number line, we see that they placed the numbers in the correct order, but 88 is much closer to 57 than it really should be. We also need students to understand the magnitude of numbers and to be able to compare them and generate a number that is greater than or less than a given number. And their range of number is up to 1,200. So for instance, you might ask your student, your child, to tell you a number that's greater than 876. And there are a lot of different responses they could give because there are a lot of numbers greater than 876. So that demonstrates their understanding of the order of numbers and how they compare with each other. You might ask them to tell you a number that is less than 1,157. Again, there's a lot of different responses they could give. So that's another skill that we want the students to develop as they're working on their number sense and starting to use the operations of addition and subtraction. So let's talk a minute about the non-standard algorithm. An algorithm is just a process, a method for doing something. And when you and I were in school, there's a good chance that you, as I, was only instructed in using the standard algorithm in addition and subtraction. And I didn't have the opportunity to really talk about those processes and to develop my own understanding. I was just given a set of steps and expected to follow them. And what happens when we do that is a lot of times the students don't develop any number sense, and they come up with wildly inaccurate answers, and it doesn't matter to them because they don't understand the numbers and what's happening to them. So research has shown that students who develop that number sense, who have the opportunity to use non-standard algorithms and to develop their own understanding of addition and subtraction, have a much greater number sense, a much greater facility with numbers. They are much better at calculations in the long run, even though it's a slower start than we probably had when we were younger. It makes a big difference in the long run. And because traditional algorithms tend to rob numbers of their value and just reduce them to a collection of digits. For instance, if I asked a student to use a traditional algorithm to add 45 plus 32, 45 is probably not even in their head when they're doing the traditional algorithm. 32 is nothing that they're considering. All they're considering is the digit 4, the digit 5, the digit 3, the digit 2, and they put them together using a set of steps. So we don't want that to happen. We want them to keep the magnitude of the numbers. We want them to understand what's happening to the numbers and not just look at them as a collection of digits and a set of steps to follow that really don't make much sense to them, that have no meaning. So we are going to let them develop these non-standard algorithms. And with this, there's a lot of different ways of approaching each problem. And we want them to approach this in a way that makes sense to them. And we're working on their number sense, we're helping them develop mental math skills, and we're developing some notation to help them express their thinking. In the traditional algorithm, again, we just kind of lose the value of the digits. You know, if we're doing 35 plus 42, we are adding a 3 and a 4, not thinking about adding 30 and 40 or 3 10s and 4 10s. So we want to help them think more deeply about the numbers. A lot of times when they get the traditional algorithm too soon, they make some mistakes. For instance, here they're adding 8 plus 4 and getting 12, 5 plus 3 and getting 8, and telling me the answer is 812, and it never occurs to them that that's not anywhere close to the correct answer. They could subtract, and we look at 62 minus 35, and quite often they just subtract with the path of least resistance. I have 2 and I need to subtract 5. Well, that doesn't make sense. So I'm just going to flip it around and subtract 5 minus 2 and get 3, and then subtract the 10s. Sometimes I've seen students who take the, especially if a problem's written horizontally like this, take the outer digits, subtract them, take the inner digits, subtract them, and then come up with an answer. So we want them to think more deeply and really think about the numbers. For instance, if I did 59 plus 25, the student can think 59 is only 1 away from 60. And 25 could be split into 1 and 24. So there's that 1 I need to get the 59 to 60. So I put 59 and 1 together and get 60. Then I take that 24 and I can split it into 20 and 4. 60 and 20 gets me to 80. I've still got that 4 from the 24. So 80 and 4 is 84. Is it a little longer than a traditional algorithm? Yes, but a student who can do this has demonstrated lots of different understandings about numbers and has used them correctly. They can do, you know, lots of different approaches to that same problem. Someone else might look at 59 plus 25 and say 50 and 20 are 70. They pull the 50 out of 59 and the 20 out of 25 and combine them. And then they say 5 can be split into 1 and 4. And they're going to take that 1 and add it to the 9 from 59 to get 10. 70 and 10 are 80. I've still got that 4 left from the 5, so 80 and 4 are 84. And they have, I haven't written any notation on here, but they have methods of recording so they can keep up with what they've used and what they haven't. And a lot of students can do this mentally and don't need any notation. They could keep the 59 together and add 20 together to get 79, add 1 to get to 80, and then take that 5 apart, get 1 and 4, add 1 to get to 80, and then the 80 and the 4 make 84. So that's 3 different approaches to that one problem. They can do the notation. Here I've shown you some of the notation. They could do 59 plus 1. And then that made them think about taking 60 and adding 20 to it. We don't put an equal sign here because 59 plus 1 is not equal to 60. plus 20. This is just a notation to show that this was my first thought, and then it led me here to think about this, and then that led me to think about the fact that I just made 80 here, and I've still got 4, so I'm going to add that 4 to the 80, which leads me to my final answer of 84. Here we're using an open number line. Remember, we talked about that earlier, and we can do the same kind of notation. I started at 59, I added 1 to it, it got me to 60. Then I added 20 to it, that got me to 80. Then I added 4 more to it, got me to 84. And you can see across here, I started at 59 and I added 21 plus 4 more, 25. I added 25 to it. When they're working with these two-digit addition and subtraction problems, sometimes they're pulling them out of word problems. And so they're going to read the word problem, and then they're going to use all the skills that they have used, mental math and notation. They can model it with a part whole model, which can also be called a strip diagram or a thinking block. They have all these different ways of modeling it, and they can solve word problems using these models. Eventually, they'll solve them with the traditional algorithm, but right now, again, we're trying to develop that number sense. Here is the part whole diagram that I was talking about. So here's the word problem. Kara had $34 in her bank account. She got some money for her birthday, and now she has $52 in her bank account. How much money did Kara get for her birthday? So the strip across the top is where we put the total. And the total amount of money she had after her birthday was $52. Part of her money she had before her birthday, and part of her money she got for her birthday. And that's the part we're trying to figure out. So again, here's a method that a student could use to solve that problem. And this helps them to organize their thoughts. Here's another one here. Henry had 62 red Legos. He used 37 of them to build a car. How many Legos does Henry have left to build a house? So again, the bar that goes all the way across, the total way across, that's where I put the total. And the total number of red Legos he has is 62. He used part of them to build a car, 37 of them. And now he's going to use the other part of them to build a house. And here's the method that he used, developing number sense, breaking numbers apart, and putting them back together. We also ask students to create their own word problems that can be solved with a given number sentence. So we give them a number sentence, for instance, 48 plus 26 equals something, and then they need to come up with a word problem that would be solved by this number sentence. And being able to do that demonstrates a lot of understanding of the structure of word problems. If you can create a word problem that matches this number sentence, then you have a lot of understanding. Here's another number sentence and a word problem that they could create that would be solved by that number sentence. They can solve problems where there's one number on this side, the sum is on the left, and then the two add-ins are on the other side. And students need to understand that it can be written this way, that the equal sign does not mean answer goes here all the time. And again, those are some different kinds of word problems that were created to match those number sentences. Well, thank you for watching. Again, I'm the math specialist at Rock Prairie Elementary. You can reach me via email at jporter@csisd.org, or you can call Rock Prairie and ask for me, and I can speak to you on the phone. There'll be a Math for Parents training for the third 9 weeks on Thursday, January 5th, 2017, and I hope to see you here. Thanks again for watching.